Assalamualaikum and hello everyone. In this video, we are going to present a topic in chapter 5 matter waves, which is the de Broglie hypothesis. This is our group members Manisha, Nur Syafiqah, Aisyah Muhammad Isham, Farah Adila, Siti Aisyah, Nazatul, Anis Nabila and Alice Rahaizan. Hi, my name is Manisha binti Harun. I will present the first subtopic, which is the pilot wave of de Broglie. Before de Broglie introduced his theory, by the early 1920s, scientists recognized that the Bohr theory has several limitations. Now the first one, as you can see in this picture, the intensity for each band is different and Bohr theory has failed to predict the observed intensities of spectral lines. The second limitation is, as you can see here, this is what we call as the Z-man effect, in which there is one spectral line that will split into three components in the presence of magnetic field. Bohr theory has failed in explaining why this situation occurs. The third limitation is it failed to explain the stuck effect, which is when the spectral line gets split up into fine lines in the presence of an electric field. The fourth limitation is it had only limited success in predicting absorption and emission wavelengths for multi-electron atoms. In this case is hydrogen atom. Not only that, it also could not be used to explain spectral lines of atoms with more than one valence electron, which is an atom that are not hydrogen like helium, lithium and oxygen. Due to these limitations of Bohr theory, de Broglie has taken the first bold step towards a new mechanics of atomic system, which leads to today's topic, de Broglie hypothesis. Before we go deeper into de Broglie hypothesis, let's take a look on the collision of ideas of physicists between matter and light. The first one is John Dalton. He discovered that matter consists of basic particles that cannot be further divided called atoms. J.J. Thomson has discovered negatively charged subatomic particles called electrons. Both of them were unable to explain the line spectrum of light that was produced by atoms. Ernest Rutherford conducts an experiment and gets three major observations from it, which are: most of the space inside the atom is empty, all the positive charges are concentrated in a very small area within the atom called nucleus, and the size of the nucleus is smaller than the atom. Isaac Newton has discovered that the particle nature of light, in which he described light as a single stream of particles, but he was unsuccessful in explaining the phenomenon of light refraction due to failure in comparing the speed of light in glass and air. James Maxwell put forth the theory that light is an electromagnetic wave. Max Planck introduced the concept of quantum, which is discrete energy. The energy in each quantum is directly proportional to the wave frequency. Albert Einstein introduced the photon concept in 1905. Einstein's quantum theory of light was successful in explaining the characteristics of the photoelectric effect that could not be explained by classical theory. Next, the most important part in this chapter is Niels Bohr and de Broglie. Niels Bohr explained the production of line spectrum by hydrogen atom. The electrons in an atom orbit around its nucleus on certain shells only. The transition of electrons from a higher energy level shell to a lower energy level shell emits photons. However, Bohr has no explanation for quantized electron, which make many scientists skeptical. De Broglie models are able to explain quantum behavior of electron that Bohr described. De Broglie could explain how quantized electron could exist, which introduced the wave-particle duality and also introduced the de Broglie hypothesis.
Now, let's proceed to know the physicists involved in this topic with me, Nur Syafiqah. Okay, who is the Louis de Broglie? He is the one of the well-known physicists in his discovery in matter, the very essence of our universe. From his name, we are know he was born in France, in which 1892. In that time, he is very charming as he born in nobility. He used this opportunity to focus on academic. For his first degree, he is originally excellent in history. He only had moderate interest for the physics subject, but his brother once shifted Louis' mind to learn physics, but he didn't force Louis to follow his step as the physician. At first, it's very difficult for Louis to learn physics because at his university not provided updated book in physics, and there is language barrier for the book from the foreign country. Furthermore, physics laboratory at his university not provide well equipped. Fortunately, his own family has the physics laboratory so that he can learn and start research on himself about the physics. He discovered many books until he able to complete his degree in science in 1913. With the breakout of World War I in Europe, he was enlisted as the army to work as radio telegraph operator in Paris. This was lead him eventually to wave mechanic. This practical experience would help him in scientific research after the war is over. After that, he worked together with his brother in X-rays. From this all experience, he was complete his doctorate thesis that's still well known until now. The outline in this thesis is determining the wave particle duality. Okay, in his work, it states all the particles can behave like wave and vice versa. In this theory become more further discovery with the development of innovation at that time and also combined with the Albert Einstein work on the photoelectric and Planck work on blackbody radiation. In Louis' perspective, what if electron behave like a wave also? This thought came out since his discovery state electrons were known as a particle mass and charge. From this, he was made a big change from previous theory, which insists that particle and waves separate each other. So, Albert Einstein endorsed Louis' work. In 1929, Louis got the Nobel Prize in Physics, which is the result of his theory with some following experiment that proved his theory in foundation for the development of quantum mechanics. This result of wave nature of electron was experimentally confirmed in 1927 by two independent laboratories in Scotland and USA via the method of electron diffractions. For the most later years, he taught at the Sorbonne University as a lecturer, and then he also published so many books for research on mechanics of wave. Fortunately, he was awarded with honorary title by so many academic institutions until at the age of 90 he was passed away in 1987.
Hello and Assalamualaikum. My name is Aisyah binti Muhammad Hisham. So today, I will explain a little bit about the formula of Louis de Broglie about the matter of wave. One day, Louis de Broglie wondered about can light behave both as a wave and a particle. He also wondered if a particle can also behave as a wave. So he tried to messing around with some of Einstein formula and see what he can come up with. So he imagined about a photo of light. If it had a mass, then its momentum would be given by P equal to the mp multiplied with c, where c is the speed of light. Now, Einstein has a lovely formula that he discovered linking mass with energy, which is E equal to mc squared. And it also used a Planck's formula, E equal to HF. So, Louis put them equal to each other. So, from the photon, we have mp equal to HF over c squared. So, we make it as equation 1. From the momentum, we have mp multiplied with c equal to p over c. So, we make it as equation 2. Now, we substitute 1 into 2. You will get P equal to HF over C. From this equation, we make it as a equation 3. Now, using the wave equation, which is C equal to F over wavelength, we substitute the equation 3 to the wave equation. So now we got wavelength equal to H over P. Okay, that's the equation. Next, the Broglie's hypothesis. So, from the Louis de Broglie, he postulates that the dual nature of the light must be expanded to all matter. This means that light possesses both particle property and wave property. In other words, all material particle possess wave light property, characterized by the wavelength, which is wavelength B, and related to the momentum P of the particle in the same way as for light. I hope you understand. Thank you for watching. The end of my part.
Hi, I am Farah Adila binti Abu Hassan. I would like to present wave properties of particle. De Broglie proposed that since photons have both wave and particle characteristics, other forms of matter also possibly possess these qualities. According to the De Broglie theory, particles with clearly defined momentum, P equal to mv, also have wavelength. And in analogy with photons, he hypothesized that particles will also have frequency that attached to it, as the formula shows E equal to hf. During that time, there was no experimental support for this theory. Therefore, he concluded that any moving matter is related to wavelength and frequency. The formula of E equals to hf is derived from the combination of the angular momentum h bar and angular frequency omega. Where we insert these two formulas into one, we can cancel off the 2 pi and then we can get the equation of E equal to hf. E is the energy of photon, h is the Planck constant, meanwhile f is the frequency of the particle. Where we insert the value into the formula, the final unit we can get is J joule because we already cancel off the unit second in the calculation. From this equation, it illustrates and presents the dual nature of matter. Particle nature in this formula are momentum and energy, and the wave nature is the wavelength and frequency. Why do we see the wave properties of material in our daily life? It is because of we don't observe the wave nature of matter. The wavelength is too small and are not relevant to people and objects. Now, let me move to the example 5.1 to get a better understanding. Why do we see the wave properties of a baseball? An object will appear with light or if it exhibits interference or diffraction, both which require scattering object or aperture of about the same size as the wavelength. From this contact, the wave light means that something shows properties of wave. Interference and diffraction are two examples of wave properties. So the statement given is a baseball of a mass 140 grams is traveling with a speed of 60 miles per hour or 37 meters per second that has a de Broglie wavelength. So here we need to calculate its wavelength. First thing first, we need to list down the information given on the statement and make sure it is in SI unit. M is 0.14 kg, H or Planck constant is 6.63 exponent negative 34 joule second, and the velocity is 27 meter per second. The formula for de Broglie wavelength is Planck constant per momentum. As we know, formula for momentum is equal to mass times velocity. Therefore, we need to replace the P with mv and insert that into the formula. Then we can get the formula of lambda or wavelength is equal to Planck constant over mv. We insert the value that we already list and we can get the final answer. De Broglie wavelength is equal to 1.7 exponent negative 34 meter. This calculation shows that the de Broglie wavelength of baseball is infinitely small. Consequently, even if they do exist, they cannot be seen and have no impact on how the microscopic object baseball moves.
De Broglie hypothesis says that matter consists of both the particle nature as well as wave nature. De Broglie wavelength lambda b is given as where represents the particle momentum and can be written as lambda b equal to h over mv, where h is the Planck constant, m is the mass of the particle, and v is the velocity of the particle. From that, it can be said that the wavelength of the matter is inversely proportional to the magnitude of the particle's linear momentum. The de Broglie equation is one of the equations that is commonly used to define the wave properties of matter. Electromagnetic radiation exhibits the dual nature of a particle having a momentum and wave expressed in frequency and wavelength. De Broglie waves are not electromagnetic waves. It's only as a guidance for the electron through space. De Broglie wavelength depends on the momentum and not on physical size of the particle. For free particle and total energy, E is kinetic energy 1/2 mv power of 2. Thus, we can get another equation lambda b equal to h over square root 2em. Let's try to answer questions. Example 1. Compute the de Broglie wavelength of the following. A 10-gram bullet traveling at 500 meters per second. We need to convert the mass to kilogram and we get 10 power of negative 2 kilogram and the velocity is 500 meters per second. Substitutes all the value in the formula lambda equal to h over mv and the answer we get is 1.3 times 10 power of negative 34 meter. For B, an electron with kinetic energy of 1 electron volt. We'll be using the equation lambda equal to h over square root 2em. And the answer is 1.2 times 10 power of negative 9 meter or 1.2 nanometer. The wavelength of the matter is extremely small and so that we cannot observe it by our eyes. Example 2. A particle of charge Q and mass m is accelerated from rest through a small potential difference V. A. Find its de Broglie wavelength assuming that the particle is non-relativistic. When a charge is accelerated from rest through a potential difference V, it gains in kinetic energy 1/2 mv squared. It must equal to the loss in potential energy QV. So we can get 1/2 mv squared equal to QV. Because P is mv, we can express this form in 2P equal to square root 2 mQV. So we need to rearrange these equations into the de Broglie wavelength. So the final equation is lambda equal to h over square root 2 mQV. B. Calculate lambda if the particle is an electron and V equal to 15 volt. We need to use the equation from part A and substitute all the value we have. And the answer we get is 1.7 times 10 power of negative 10 meter or 1.7 angstrom. This wavelength is of the order of atomic dimensions and the spacing between atoms is a solid. Such low-energy electrons are routinely used in electron diffraction experiments to determine the atomic positions on a surface.
The principle of complementarity was announced in 1928 by the Danish physicist Niels Bohr. Depending on the experimental arrangement, the behavior of such phenomena is like an electron is sometimes wavelength and sometimes particle-like. Such things have a wave-particle duality. It is impossible to observe both the wave and particle aspect simultaneously. Together, however, they present a fuller description than either of the two taken alone. In effect, the complementary principle implies that phenomena on the atomic and subatomic scale are not strictly like large-scale particles or wave. The complementary principle wave-particle duality does not mean that a photon or a particle is both a wave and a particle simultaneously, but there is either a wave or particle aspect depending on the situation or circumstances. De Broglie's explanation of the quantization in the Bohr's atom. De Broglie came up with an explanation for why the angular momentum might be quantized in the manner Bohr assumed it was. De Broglie realized that if you use the wavelength associated with the electron and assume that an integral number of wavelengths must fit in the circumference of an orbit, you get the same quantized angular momenta that Bohr did. The circumference of the circular orbit must be an integral number of the wavelength, 2 pi r equal to n lambda equal to nh over p, while lambda is equal to h over p. The momentum p is simply mv as long as we are talking about the non-relativistic speed, so this becomes 2 pi r equal to nh over mv. Rearranging this a little gives the Bohr's relationship Lr equal to mvr equal to nh over 2 pi. From that equation, we got L equal to mvr equal to nh, lambda b equal to h over p equal to h over mv, then mv equal to h over lambda b, then r equal to nh over h lambda b equal to n lambda b over 2 pi. Then we got 2 pi r equal to n lambda b, where r is the radius of the orbit.
So next is de Broglie's theory of matter waves. So de Broglie applied the concept of matter waves to the structure of the atom. He postulated that electrons orbit the nucleus as standing wave, which is stationary waves. So when electrons behave as standing waves, they are no longer emit energy in the form of radiation, since this applies to particles. Therefore, de Broglie's matter wave theory provided an explanation for Bohr's first postulate, which is electrons orbit the nucleus in stationary states and do not emit energy. So this is the Bohr postulate atom. Next is circumference of an electron orbit is quantized, meaning it is an integral multiple of the wavelength of the electron wave. So this is the formula where the n is the integer denoting the energy level. Next, so this figure shows changes in electron wavelength with energy level. So the number of antinode, which is the crest antinode, and correspond to the principal quantum number, which is n, and it is simply defines the energy level. So this is the antinode, the crest antinode. So for example, the circumference of the n equal to 1 orbit equal to 1 wavelength of the electron wave. The circumference of the n equal to 2 orbit equals to 2 wavelengths of the electron wave. You can see like this example. So the implication of this is the circumference and the radius of an electron orbit must equal to the specific values, as otherwise standing waves cannot form. If the standing wave cannot form, it's going to become like this and this. This is a standing wave which is cannot form. It cannot form properly like this figure. So lastly, combining the matter wave equation and quantization of an electron orbit circumference gives 2 pi r n equal to nh over mv. Then we're going to get this equation, which is this equation shows that the angular momentum of an electron is an integral multiple of h equal to h over 2 pi. Therefore, de Broglie's matter wave theory supports Bohr's third postulate, which is the angular momentum of an electron is quantized.
Assalamualaikum, my name is Elis Rahaizan binti Abdurrahim. Firstly, I will explain about electron standing waves and the Bohr model. De Broglie applied the concept of matter waves to the structure of the atom. He postulated that electrons orbit the nucleus as standing waves, which can also be known as stationary waves. Standing waves are formed as a result of interference between two waves of equal frequency and amplitude traveling in opposite directions. De Broglie explained that when electrons behave as standing waves, they no longer emit energy in the form of radiation, since this applies to particles. Therefore, de Broglie's matter wave theory provided an explanation for Bohr's first postulate, where electrons orbit the nucleus in stationary states and do not emit energy. Figure 1 shows a simple scenario in which a standing wave is created when two out-of-phase waves are oscillating between two reflective surfaces. Bohr's suggestion that orbital angular momentum of electrons is quantized is equivalent to the requirement that an integer number of de Broglie wavelengths must fit into the electron orbit. As you can see in the figure, it shows the visualization of electron waves, where n is an integer denoting the energy level. Let's take a look at the visualization for n equals to 3, the green one. We can see that the standing waves fit to a circular Bohr orbit. In this particular diagram, 3 wavelengths are fit to the orbit corresponding to the n equals to 3 energy state of the Bohr theory. Another aspect of the Bohr theory that is also easier to visualize physically by using de Broglie's hypothesis is the quantization of angular momentum. One simply assumes that the allowed Bohr orbits arise because the electron matter waves interfere constructively when an integral number of wavelengths exactly fits into the circumference of a circular orbit. This is represented by the following equation: 2 pi r equals to n lambda, where r is the radius of the orbit. For example, the circumference of the n equals to 1 orbit equals to 1 wavelength of the electron wave. The circumference of the n equals to 2 orbit equals to 2 wavelengths of the electron wave. The implication of this is that the circumference and radius of an electron orbit must equal to specific values, as otherwise standing waves cannot form. The figure shows changes in electron wavelength with energy level. The number of antinode crests corresponds to the principal quantum number n, where n simply defines the energy level. Combining the matter wave equation and quantization of an electron orbit circumference gives L equals to nh over 2 pi. This equation shows that the angular momentum of an electron is an integral multiple of h over 2 pi. Therefore, de Broglie's matter wave theory supports Bohr's third postulate, which states that angular momentum of an electron is quantized. In 1927, C.J. Davison and L.H. Germer verified the de Broglie hypothesis directly by observing interference patterns, a characteristic of waves with electron beams. The de Broglie's hypothesis predicts that one should see diffraction and interference of matter waves. For example, we should observe electron diffraction and atom or molecule diffraction.